Hello, welcome back to Compressible Flow. I'm Professor Steve Miller. Today we'll be talking our discussion on hypersonics. We will look at Newton's theory, his corpuscular theory. Then we'll talk and derive the so-called K or similarity law of hypersonics, which is similarity parameter, which is very similar to the transonic one, but it wasn't derived by Newton. It was derived by a contemporary genius who was rejected by the country of the United States. We then look at particular isentropic relations, oblique shock relations, and expansions based on this brilliant theory from an immigrant to our country, which we rejected. We'll see how all the assumptions break down that we made previously, but we'll recover very similar relations of the three major flow phenomena which we derived and talked about earlier, all in one class. Let's get started. I like to start with a particular quote because it's so relevant to the subject and the major breakthrough in the field. It reads, "I do not plan to come back. I have no reason to come back. I plan to do my best to help the Chinese people build up the nation to where they can live with dignity and happiness." This was written by Qian in 1955 to reporters after returning to China. And it's cited in, of course, an obituary in where he established the Jet Propulsion Lab in the United States. The U.S. government prosecuted this person and treated him for Chinese spies. Of course, he was a genius who helped build up the American program and establish the basic theory and breakthroughs of hypersonics. We'll talk about him in a bit. Let's talk about a few more quotes about him first. Here's one by Dan A. Kimball in the 1950s. In the book, Thread of the Silkworm. "It was the stupidest thing this country ever did," and we're referring to the United States. "He was no more a communist than I was, and we were forcing him to go." Here's another quote from Grant Cooper of Caltech, who was an attorney in the 1950s. He wrote that the government, that is the US government, permitted this genius, this scientific genius, to be sent to communist China to pick his brains is one of the tragedies of this century. This is probably a life lesson for us today, where we look at particular intelligent, hardworking people and let them leave the United States. Let's look at particular corpuscular flows. These might be viewed as a hypersonic or hypervelocity flow, or any other type of flow. This is the so-called corpuscular model of flow. Let's say we have a flat plate, and look at our flat plate problem. And we put in a number of particles moving from left to right, and we hold the plate stationary. Each particle might be, say, a molecular fluid. This is indeed Isaac Newton's viewpoint of fluids, which is entirely inaccurate because, of course, this was found and proposed well before the idea of the atomic models. You can see here the particles come in from the left and they bounce off just like a Newtonian flow off the plate and go in a different direction. They indeed impart a momentum on the plate which might explain lift. The particles that travel above the plate are never influenced by the plate and they just keep moving from left to right, as you see in this particular model. Indeed, behind the plate there would indeed be a vacuum, but we know from our aerodynamic measurements that indeed the fluid wraps around the plate and remains attached. There's no vacuum that occurs even in bluff body, subsonic, creeping flows, transonic flows, or even low-speed supersonic flows, or high-speed supersonic flows, or even low-speed hypersonic flows. So this theory gave the wrong predictions, but yet it was a brilliant idea and model. Let's look at the type of ideas that, of course, could be used for hypervelocity type flows with the corpuscular model. This was all proposed by Isaac Newton, and we finally come to him in our history lesson. He lived from 1642 to 1726, and of course he was English. I'm sure everybody's heard of him, and no doubt he was a mathematician, astronomer, theologian, and physicist. In fact, in 1687, he published Mathematical Principles of Natural Philosophy, which laid down the idea of calculus. He theoretically derived the speed of sound, though it had some error, and introduced the notion of a Newtonian fluid, which, of course, we use today to describe a lot of fluids with linear stress-strain relationships. He also invented what I just showed as the essence of the corpuscular theory of fluid, and of course he has many other countless accomplishments. Voltaire said, "He was never sensible in any passion, was not subject to the common frailties of mankind, nor had any comments with women. a circumstance which was assured me by the physician and surgeon who attended him in his last moments. A curious quote about an Englishman by a Frenchman. There he is in his oil painting, and we'll continue to look at his corpuscular theory, because of course its relevance to aerodynamics. In fact, it's a failure in aerodynamic theory, but maybe has some bearing in hypervelocity flows and hypersonics. Let's look at the implications of Newton's theory, which you can derive easily simply by using his momentum laws against the plate with particular randomly injected particles. And you'll find these relations for coefficient of lift and drag respectively from corpuscular theory. The coefficient of lift will go as 2 times the square of the sine of the angle of attack, and the coefficient of drag on a flat plate will go as 2 times the sine cubed of the angle of attack, where the angle of attack is alpha. So you can see, indeed, there's almost no change in the velocities of the particles because, of course, they import momentum and bounce off the plate, and they have very little mass. The method of characteristics does indeed work sometimes for solving hypersonic problems. We'll assume that the hypersonic flow will consist of small perturbations of flow relative to the parallel uniform stream, much like the corpuscular theory. And we'll look for similar laws for 2D and axisymmetric flows in this class. For example, let's consider a two-dimensional irrotational motion past a thin profile, where the stream is initially uniform in parallel. That's the uniform inlet condition around the body. That's its uniform parallel flow, just like we have earlier in this class. Now, the error between Newton's corpuscular theory and the theory with large disturbances, which actually happens in hypersonics, is indeed goes as, say, delta squared, where delta is the thickness ratio of our particular body. That's the thickness divided by the chord, for instance. In supersonic flows, we see that the error goes as, say, delta. In transonic flows, it might go as delta to the two-thirds. But Newton's theory will suggest that particles striking the surface will lose their cross-stream momentum. Let's draw a little picture of this. According to Newton's corpuscular theory, we'll have a particular coefficient of pressure on the airfoil that goes as 2 sine squared alpha against the whole chord C. On the other side, according to his theory, we have a vacuum, and we might say C sub P is about 0. And so we do have a normal force only on the plate, which translates to the lift and drag, where we can define and derive CL and CD respectively. It's a simple calculation. Now let's look at the results of Newton's theory on a particular flat plate. On the x-axis, we have the angle of attack of the flat plate from 0 to 90 degrees. And so we showed the picture with a very small angle of attack around, say, 3 or 4 degrees down here. The left y-axis is the coefficient of lift, and the right y-axis is the coefficient of drag. We showed the coefficient of drag as this solid line, the coefficient of lift is this solid line, and the lift over drag ratio as this decaying line as we approach 90 degrees to go to 0. So this all makes well and good sense. But unfortunately, it does not follow what we find in practice, though it does follow rough trends for slender bodies at hypervelocity high speeds. Let's look at Newton's method with actual measurements of pressure coefficient on a wedge and a cone placed in a hypersonic flow with a half angle of 15 degrees respectively. On the x-axis, we have Mach number from 0 to 4, 8, 12, 16, and 20. On the y-axis, we have C sub P from 0 to, say, 0.6. At low Mach numbers, say between 0 and 4 or maybe 8, there's a lot of variation, of course, of CP on our wedge and cone respectively, which falls off. Newton's theory, of course, predicts a constant CP value across all Mach numbers with increasing velocity. This is rather troublesome, but you can see at high Mach numbers, we observe a Mach number independence, just as we noted in our previous class on the philosophy and physics of hypersonic flow. Indeed, the cone case and Newton's case actually come to a rather close CP value from the simpler calculations. Indeed, today there's simulations called DSMC, Direct Monte Carlo Simulation, and indeed these simulations use particulates and statistical theories to derive rarefied flow fields. So though Newton's method is not used exactly today, there is a contemporary approach for rarefied flows where we model the particles instead of the continuum based on the Knudsen number calculation. This is the best we could have done with these types of theories through the early 1930s and 40s and even early 50s, and everybody was rather stuck on the problem, and we had trouble going forward. This is where a lone genius came in, working with two of the smartest people in aerodynamic theory at the time. His name was Xu Xian. We'll call him Dr. Xian for now. He was alive from 1911 to 2009, so he didn't pass away too long ago. Indeed, he was born in China and came to the United States to study. He was considered a genius in aerodynamics and hypersonic theory and many other subjects. He got his MIT Ph.D., where he joined later at Caltech, Dr. Theodor von Karman's group, and he helped Dr. Karman found and create the NASA Jet Propulsion Lab, which of course exists today. In the 1950s, the United States government accused Dr. Xian of communist sympathies, but there's no evidence of this even today. In fact, in 1950, despite protests by his colleagues at Caltech and NASA JPL, he was stripped of his security clearances. Here, Dr. Xian decided to return to China, even after being housed in a friend's house because they took away his house, and he was detained in a terminal island near Los Angeles. After 5 years of house arrest by the United States government, Dr. Xian was released in exchange for a repatriation of American pilots. He returned to China and helped lead the Chinese nuclear weapons program, and ultimately created the Chinese program, which became, of course, the third atomic state in the world. He married Xian Ying, a famed opera singer. I think the real message of this story is, of course, that if you are a genius in aerodynamics, you too might be able to marry a famous opera singer. Nonetheless, here's two particular pictures of him. On the top is him showing a ballistic missile and glide trajectory from a launch location to Paris. In the lower right photo is one of my favorite photos, where we see the three top aerodynamicists in the world at the time, meeting after World War II. We see Dr. Ludwig Prandtl, his student, Dr. Theodor von Karman, and of course, Dr. Theodor von Karman's one of his lead researchers, Dr. Xian, all in the back of a Jeep touring Germany. So you can see these three people were academically related and were the leaders in their field in the United States, Germany, and China, respectively. Let's now look at the idea and philosophy of the breakthrough work of a true genius, Dr. Xian. He analyzed hypersonics with the velocity potential approach, which, as you can see, is indeed a nonlinear approach, for compressible perturbation of velocity potential phi s. And so this is written as a perturbation about the flow, just like we found in transonics. This equation reads 1 minus u squared over c squared. U is the local velocity in the x direction, and c is the speed of sound locally. Phi is the velocity perturbation potential. V, of course, is the velocity component in the cross-stream direction. And those are all the variables, I guess. There's no other variables. So you can look at this equation. Of course, this equation can be derived from the Navier-Stokes equations given certain assumptions. In fact, many of the assumptions are the same as transonic flow. Here, u is related to the ambient velocity, u infinity, which is likely much larger than the perturbation, which is d phi dx, which is the velocity perturbation change in the x direction. We also define a value r, which is d phi dy. Let's try and continue this analysis. So this is the equation you started with, which governs the perturbation of velocity about a very, very high speed flow, and it's compressible. In this equation, we can also find the speed of sound relative to the ambient speed of sound and velocity. So c squared goes to c sub infinity squared minus gamma minus 1 over 2 times u squared minus v squared minus u infinity squared. We've made no assumption of gamma. It doesn't have to be 1.4 like in hypersonics. It could change with temperature if we desired, which is equal to c infinity squared minus gamma minus 1 over 2. And now we substitute in for u and v the derivatives of the velocity perturbation, which are defined in, of course, 688, 689. Now remember, u infinity must be much greater than c infinity because we're in a hypersonic flow. That is, Mach number is very large. U infinity should be much larger than d phi dx, and U infinity should be much larger than d phi dy. So we can substitute these three relations into our previously developed equations of 687 and 691 and substitute and simplify, and Dr. Cian found 692, which involves gamma, Mach number, C infinity, phi, its derivatives, and of course is all equal to 0. So we're not out to solve this equation yet, but we're looking to analyze it, because remember at the time there's no computers that could analyze this equation. We'll now let our non-dimensional variables be and non-dimensionalize the equation as psi will be x over L, where L is the chord, and x is the streamline's position, and eta as y over L over delta. Y is the cross-term direction, L is the chord, and delta will be the thickness ratio. Here, eta is normal to the body, and phi will be non-dimensionalized accordingly with these two non-dimensional parameters as C infinity L over M infinity times a function of psi and eta. So this was our choice, and it was a very intelligent choice, and you'll see in a second why. Using these definitions in 693 and 694, we can make the substitution into 692 of the equation in the slide deck, and you'll find equation 695. Here we have 1 minus gamma minus 1 of df d eta, psi, minus gamma plus 1 all over 2 m infinity delta squared times df d eta squared, all times d2f d eta squared. And it's equal to the right-hand side of m infinity delta squared times d2f d eta squared plus 2 df d eta times d2f d eta, d psi dy. Now take a few seconds and this y here must be an eta. Excuse my typo. So take a few seconds and consider why Dr. Cian made this non-dimensionalization using this particular equation. Look at the particular terms in the equation in 695. What do you see? Take a few seconds to think about it. You might have seen that there's a particular form of this equation where there's a similarity rule that exists. And if you haven't seen that, you can see why, of course, Dr. Cian might be considered a genius. He could look at this equation and pick out the fundamental physics. He wrote in a translation, if a series of profiles having the same thickness distribution but different thickness ratios are placed in flows of different Mach numbers, such that m infinity is held constant, then flow patterns are similar in the sense that they are governed by the function f of eta. So looking at this equation and this similarity rule statement, which you should read carefully and consider, we can look at the terms m infinity and delta, because if partial f and partial eta are finely related. We might write that m infinity delta is therefore the hypersonic sensitivity parameter k, and we would let k equals m infinity delta, which we could of course substitute in 695 here and here. And of course, then the rest of the relations are finely related, as long as k remains the same. Here, delta is the thickness ratio, and about unity, for most flows, this equation will hold. So therefore, we can create and argue that there's a mathematical definition of hypersonic flows based on the hypersonic sensitivity parameter. We'll define a hypersonic flow mathematically as a supersonic flow with small perturbations for which m infinity delta is unity or greater. So if k is unity or greater, then indeed it's a hypersonic flow. You can see how this works. For high values of Mach number, of course, k will be large. On the other hand, for very large thickness ratio, as in small Mach numbers, we might also see a hypersonic flow. This helps us understand why, in hypersonics, we might view the shock waves as being very close to the turning angle of the vehicle from its leading edge. This equation is indeed shown through mathematical rigor by Dr. Cian as a system of finely connected profiles. Affinely means allowing for preserving parallel relationships. So if we have a wind tunnel test and look at 695, and we can solve this equation based on a particular k or measured values and transform them to f, we can find through an inverse transformation at full scale, holding k constant, what happens in the flight vehicle in the atmosphere. Let's look at some particular plots of the hypersonic sensitivity parameter to understand it physically. And I think this helps many students understand the physics. Here we have a range of applicability of similarity laws for cone cylinder and Gibbs cylinders, which are particular cylinder shapes. We have, of course, the fineness ratio F, which is related to delta. On the y-axis, we have Mach number in infinity, and we have, say, k 0.51 and 2. You can see they actually paint out straight lines with increasing Mach number and fineness ratio. Let's now plot the longitudinal coordinate on percent nose for pressure distributions against the hypersonic similarity law for the O-Gibbs cylinders. These indeed are based on the solutions of various and matched K in equation 695. You can see the y-axis has P minus P infinity over P infinity. So we're looking at a static pressure variation on the longitudinal coordinate of the nose from 0 all the way to, say, 200% of its nose length, as shown in here. You can see these are three shapes, three independent shapes, but they all have the same ratio of K equals 1, because, of course, K equals M times delta, and F is a function in delta. So we'll have K equals 1 for the first, where M equals 3, K equals 1 for the second cone, where M equals 6, and K equals 1 for the third cone, where M equals 9. So we actually find the same pressure coefficient along the body of the normalized cone, according to the theory. The measurements for these three cones are circles, triangles, and squares, respectively, for Mach 3, 6, and 9, and they follow a perfect curve. The solid line, of course, is the solution from the similarity equation in equation 695, which we just showed, for a given value of K equals 1. So you can see there's a whole family of solutions in collapse. This means that if we have a particular Mach number and fineness ratio in the wind tunnel, and then we fly at a higher Mach number like 9 and change the fineness ratio, we can exactly predict through similarity theory from our wind tunnel flight test the pressures on the device. It's a brilliant idea, which revolutionized, of course, the experiments and work in hypersonics. Let's do the exact same thing for a different parameter for 5 different cones with 5 different vertex angles. Here the x-axis is K, normalized by M infinity over F, and the y-axis is the pressure on the cone. And of course, once again, we're increasing K, and we can look at a whole value and range of experiments where we collapse K on these particular curves. Here, the lines, of course, are theory, and all the experiments are symbols. So now that Dr. Cien developed this hypersonic similarity theory and collapsed all the data they knew about hypersonics from different wind tunnel tests for various geometries, he then set out to try and refine isentropic relations, oblique shockwave relations, and expansion relations for hypersonics, which differ from the traditional theory which we developed in this class that came out of Prandtl and Meyer in Germany. Here we have the original relation. We want to find P over P infinity with respect to Mach number. Let's write P over P naught divided by P infinity over P naught. So we've just rewritten the same equation. In the numerator and denominator, we'll simply substitute in values for P over P naught and P infinity over P naught. We'll take Mach number and substitute it as U squared plus V squared over C squared in the numerator. Now remember, for pressure coefficient, we have redefined U and V, and of course C squared, as U infinity as partial phi partial x, partial phi partial I, and of course C squared we rewrote with psi and eta, and phi we defined as C infinity F over M. We can then refine and redefine C sub P as P minus P infinity divided by dynamic pressure. We can rewrite the dynamic pressure again as gamma M squared, and we can rewrite the right-hand side. So we've done this in this class. Now we can expand CP in powers and disregard higher order terms, because of course they'll be smaller and negligible. We can then relate to the thickness distribution these particular pressure ratios solved for P minus P infinity. We can then make the substitution, and then we find CP as a function of the hypersonic similarity parameter and the affine relations, dF d psi and dF d eta. So you can see now we're predicting completely the pressure coefficient on the distribution of the vehicle only in terms of the hypersonic similarity parameter, Mach number, and the fine relation, which we might find, of course, from a wind tunnel test. You'll see indeed in this particular equation that F only depends on psi and eta, which can be seen here in these equations. And Cp over delta squared and Cp m infinity squared are only dependent on the hypersonic similarity parameter for particular profiles with the same thickness distribution. Therefore, the camber of the vehicle and angle of attack must be proportional to delta. Therefore, we can rewrite our traditional relations of aerodynamic theory, which you learned in your previous classes, for hypersonic vehicles for two finely related profiles. We'll have the coefficient of goes as 1 over m infinity squared times the hypersonic similarity parameter squared times some affine relation of lift, which is only a function of mainly the hypersonic similarity parameter with the shock with gamma. You can write the same term for drag, but with 1 over m cubed, and the same type of functional form for the coefficient of moment as 1 over m infinity squared. So just like Newton's corpuscular theory, we're finding a square and cubed relation. Just like he had sine squared and sine cubed with lift and drag, here we're finding m squared and m cubed. That's curious. Let's look at an example of the most basic application of Dr. Cien's technique. Let a symmetric profile with thickness ratio of delta 0.1 be tested at m infinity of 5 and angle of attack 5 degrees. Measurements will yield the corresponding values of CL and CD1. What can we say about the same profile with a different thickness ratio of 0.05? Well, it's simple. Since it's a similarity parameter, we must equate them at the same value for the flight test and experiment. We'll set m infinity 1 delta 1 equals m infinity 2 delta 2, which of course is equating k1 equals to k2. The data of the second profile will always depend at least at m infinity 2 equals 10 by substituting in, of course, delta 1 and delta 2 and m infinity 1. We can then say that alpha 2 over alpha 1 goes as delta 2 over delta 1, and so the equivalent angle of attack of the vehicle will be 2.5 degrees, according to, of course, the ratios we showed earlier. The lift and drag coefficients corresponding to delta 2 of 0.05 and m2 at 10, which we just found, and angle of attack of 2.5 from equation 703, will be related to the first condition by the following ratios, where the lift coefficients will go as the square of the ratio delta and the drag coefficients will go as the cube root of delta. Try and do this most simple example yourself of relating through similarity theory, the hypersonic similarity parameter, for the simple test and experiment of the most simple device. So we've found CLCD and CM. We now want to find oblique shock relations for hypersonic flows. We can find these oblique shock relations through the same type of approach we previously showed. It'd be a lot of math, so let me summarize the approach for you. We might have our pressure ratios will go as 2 alpha over alpha plus 1, m1 sine squared beta minus alpha minus 1 over alpha plus 1. This is basically our shock relations for high speed. Now, we'll let beta be the shock angle and theta be the turning angle. So we want to find the pressure coefficient across a shock. We can then take 706 and substitute in our, of course, wave angle beta and our turning angle. And through some simplifications, we'll find 4 over alpha plus 1 of sine squared beta minus 1 over m1 squared. We can then find m1 as only a function of beta alpha and del theta s, and you'll find 708 of 1 over m1 squared, that's the Mach number in front of the shock, will be sine squared beta minus alpha plus 1 over 2 times sine beta sine theta all over cosine beta minus theta s. So we can now observe another form of the pressure coefficient behind a shock. We'll have 1/4 CPS squared cosine 2 beta minus 1 minus CPS over 2 squared sine squared beta tangent theta s, where the sub s denotes a shock wave turning angle. We'll introduce, of course, the assumption that m1 is large and theta is small, as we see in hypersonic calculations. We have high incoming Mach numbers to the shocks, and we have very low turning angles. That means Cp will be small relative to unity, beta will be small, and therefore cosine of the angle will be about 1, and the tangent of the turning angle of the shock will be about the turning angle of the shock, which is small angle theory. Therefore, we can approximate the pressure coefficient across a shock as 1/4 c sub p of theta s squared sine squared beta, which will be theta s squared of alpha plus 1/4 cp plus 1/m1 squared, where alpha is the turning angle. We can try and place this in a form of the hypersonic similarity relations, which we showed in this class. We'll try and show that Ks might be m1 theta instead of delta. So we'll define a new hypersonic similarity parameter, Ks. The sub s stands for shock. M1 is the Mach number in front of the shock, and theta s is the turning angle of the shock. And then we can show, using Cp, we can show, indeed, that Cp will go as theta s, that's the turning angle that created the shock squared, times some fine ratio of P of K and alpha, where K equals m1 theta s. Now we can substitute equation 711 into 710 on the previous page and find Ps squared minus gamma plus 1 times Ps minus 4 over Ks squared is 0. Indeed, if we look at this equation, Dr. Cien proposed that we have a quadratic solution. The shock pressure will go as gamma plus 1 over 2 plus the square root of gamma plus 1 over 2 squared plus 2 over K squared. Only the positive solution is useful, of course, because we want pressure to rise. Just like we had multiple solutions in theta beta Mach number, we choose the positive real root. With the same approximation, we can then find the Mach numbers across the shock. m2 over m1 will go as the square root, inverse square root, of 1 plus gamma over 2 k squared times p, which we showed and introduced in 711. This is the form of the function of special geometry of an oblique shock for hypersonics. If we let Mach number become very large, which is for hypersonic flows, we can find the simplest relations for m, which will, of course, be very large, and hypersonic similarity parameter for shock will go to a very large value. We'll find the pressure coefficient goes as gamma plus 1 times the turning angle of the shock squared. The coefficient of lift will go as the same. The coefficient of drag will be approximate the coefficient of lift on an order of magnitude. What's amazing about these values, if you recall Newton's corpuscular theory, will that be, if we set gamma 1, we'll exactly recover Newton's theory. Look at, of course, Cp and Cl and compare it to Newton's theory. Indeed, all these have limiting values, which go to an asymptotics as m infinity goes to 1. In fact, the Mach number after the shock, with a turning angle theta s, can be approximated as 2 divided by the shock angle theta s, divided by square root of gamma times gamma plus 1 in 715. We now summarize the shock wave parameters for hypersonic flow. Here's a typical shock with m1, p1, rho 1, t1 in front of it. And after we have u2, p2, rho 2, t2, and m2. On the right, we summarize the relations, which we just showed the overview of the derivation, but not in detail. That's beyond the scope of this class. Let's now look at the expansion waves. An incoming Mach number will be very large in hypersonics and will become even larger after it goes through an expansion. Remember, expansion waves accelerate a flow, so we should expect m2 to be greater than m1. Our theory of expansions derived by Theodore Prandtl was indeed exact, and here it is repeated in equation 716 of the slide deck. We have the turning angle of the Prandtl-Meyer expansion goes as all these values of gamma and, of course, m squared in m. Now, m is the local Mach number, and mi is the beginning of the expansion. So m sub I is the initial Mach number at state 1, and m is the Mach number after part of the expansion. Since m and mi are very large, we might say that the square root of m squared minus 1 and the square root of mi squared minus 1 are both approximately m and mi, respectively. You can review, of course, the Prandtl-Meyer expansion theory, which we presented in this class a few lectures ago, to remember and understand the formation of 716, which made no assumptions about the type of gas law used. And so we can use it again here in hypersonics. Again, that's exactly what Dr. Cien did in his analysis. Let's now make our high Mach number assumption and substitution into 716 from, of course, the previous equation. 717, and we'll get a simplified form of the turning angle of the expansion, which we write as sub E. It's equation 718. We can also look at the pressure ratios we derived from the expansion theory. We'll write those directly down in 719 and make the same substitution. Recall the pressure changes across the expansion as a function of m and mi. Here's the substitution, and through the high Mach number assumption in 717, we can reduce it to mi over m of 2 gamma over gamma minus 1. We can now solve in 719 for m and place it into equation for 718. We then get equation 720. On the left-hand side, we'll place, through a rearrangement, mi times theta I, that's the Mach number times the turning angle, will go as a function of pressures before and after the shock respectively, and of course the Mach number in front of the shock. Why did we put it in this form? As you can see on the left-hand side, we have derived a hypersonic similarity parameter for the Mach number and turning angle, which is like for expansions, just like we had one for shocks. Now remember, the Mach number is large, so the first term is absolutely dominant in equation 720. As you see here, 1 over 3 mi squared is very, very large, and 1 over a large value is very small relative to the first term. So that means we can dump the second term of the previous equation, and we'll let Ke, the hypersonic similarity parameter of the expansion, be mi times theta I, the Mach number in front of the expansion times the turning angle of the expansion. And therefore, we can find the pressure drop across the expansion. P divided by P in front of the expansion will go as 1 minus gamma minus 1 over 2 times K sub E times 2 gamma over gamma minus 1. Recall that we showed that Cp equals 2 over gamma m times P over Pi minus 1. From, of course, the oblique shock part of this class. We can then make the substitution of P over Pi into the pressure coefficient for the expansion and expand out and simplify, and we'll get C sub P of 2 over gamma K squared times 1 minus gamma minus 1 over 2 times K, 2 gamma over gamma minus 1 to the power minus 1 all times theta E squared. So this is the pressure coefficient variation through an expansion. Here, K is the hypersonic similarity parameter for expansion waves, which is m times theta E. Now, it's true that this equation is valid for all values of Ke, which are less than or equal to 2 over gamma minus 1. If we let K equal 2 over gamma minus 1, then the pressure goes to 0 and we find a vacuum. And indeed, the Mach number after the expansion becomes infinity, just like we showed in the asymptotic analysis in our Prandtl-Meyer expansion wave classes. Indeed, this is physically a vacuum which exists in the flow, which corresponds to Newton's corpuscular theory once again, but of course it's a more exact theory. Let's look at some particular examples of the oblique and expansion theory for Cp with respect to K. The exact solutions are written as solid lines. A linearized theory is a dashed line. And the theory, with of course second order terms included, are the dashed dot line. Measurements are symbols. You can see the top set of lines are shocks, and the bottom set of lines are expansions. So this solid line with solid dots, with solid circles, is the shock theory, and it exactly aligns with Cp versus K, similarity parameter for shock and expansion respectively. The second line here, solid line with dots, are the experiments and theory of Dr. Cien for expansions. And you see, we have corrected and overcome the gas assumptions of the traditional theory for high-speed flows given very large Mach numbers and matching similarity parameters K for shocks and expansions respectively. Let's summarize now the performance of two-dimensional profiles. Now that we derive CL, CD, CP, we might write CL, CD, and C moment as integrals of the pressures with respect to the profiles defined in the affine relations. For example, coefficient of lift will be as 1 over L, which is the chord, times the surface integral of Cp dx. The same can be written for CD and, of course, the coefficient moment. Now, for a plate with an upper edge and no shock, like we showed in the flat plate case, Mi will be M infinity, and Pi will be P infinity, and theta E will be ample, which will turn the flow through the expansion. From our coefficient of pressure equation for the expansion, we'll find 727 upon substitutions. Remember, K equals delta M infinity. delta is the thickness ratio, and delta will be proportional to the angle of attack. Therefore, we can make the approximation from 727 to 728 of the following equation. We can write Cp over delta squared will go as 2 over gamma k squared times the quantity, 1 minus gamma minus 1 over 2 ke squared, to the 2 gamma over gamma minus 1 power minus 1. So you can see we made the substitution for the expansion. Now with a lower edge, there'll be a shock, and we need to apply Cp to the shock equation. We need to know the conditions just behind the shock, because it's a marching problem for the flat plate case. We will once again use the developed hypersonic relations and find the following pressure coefficient, which we showed in this class, using the same assumptions. Remember, the pressure ratios will be, which we derived in this class for the shock, of 1 plus gamma minus 1 over 2k times 2 gamma over gamma minus 1. And we found Cp with the shock upon substitution of the pressure into 729 of 4 over gamma plus 1 times sine squared minus 1 minus m1 squared, where of course this value is the turning angle of the shock. Once again, the hypersonic similarity parameter is m delta, where that's the thickness ratio. Upon substitution of these equations and simplifying, just as we did for the expansion, we'll find the pressure coefficient for the shock. The pressure coefficient for the shock divided by the thickness ratio squared will go as k, similarity parameter of the shock squared, divided by the similarity parameter of the flow squared, times the pressure of the shock, plus 2 over gamma k squared, all times 1 plus gamma minus 1 over 2 ke squared, which is the expansion similarity parameter, all times 2 gamma over gamma minus 1 minus 2 over 2 gamma k squared. So you can see now we've combined the coefficient of pressures from the shock and expansion into one single equation. This means that there's similarity of simple wave expansion and shock waves for a given m1 and theta through equation 730 for a typical slender hypersonic vehicle at a small angle of attack. Let's examine some particular results of this complicated theory. Let's let alpha be our angle of attack, and we'll let k equals m infinity alpha. For the upper and lower surfaces, we'll let delta equal to alpha, and therefore ke will be equal to k, and ks will be equal to k. And therefore ke, ks, and k are all equal to m infinity alpha. That's easy, and that's a good assumption to apply to 730. We'll then find this particular equation upon substitutions. The coefficient of lift divided by the angle of attack squared is equal to the coefficient of drag divided by the angle of attack cubed, which follows Newton's corpuscular theory, will all be equal to the right-hand side, which is a function of the ratio of specific heats and hypersonic similarity. We now found a single equation relates the experimental coefficient of lift and drag for slender bodies at low angle of attack with flight vehicles as long as we match k, the hypersonic similarity parameter, which is equal to the Mach number angle of attack. Let's now look at the application on an actual flat plate experiment. The lift curve, of course, will be very linear for low m infinity, and will become quickly parabolic as we increase m infinity. As m infinity becomes very large, we'll let and see that the coefficient of lift goes as gamma plus 1 times alpha squared, which we showed in this class. In the incompressible flow case, you'll have recalled from your previous classes that coefficient of lift goes as 2 pi times the angle of attack. Figure 456 of the slide deck illustrates these concepts. We have lines of particular coefficient of lift and CD normalized with respect to angle for different Mach numbers. You can see the incompressible result is almost exactly recovered as the Mach number goes to 0. As the Mach number goes higher and higher, we recover the experimental results. Let's now consider profiles thickness. Unfortunately, there's no easy way to find analytically profiles of thickness, but we can with measurements show the following finely related properties. For a value of, say, delta, the thickness ratio, we might regard plots of coefficient of lift for alpha for a particular m infinity. On the x-axis, we have our particular angle of attack normalized with delta, and the y-axis coefficient of lift divided by the thickness ratio squared. You'll see in this case we have a single wedge with a little hat on top, with a small angle of attack. Here we show a family of solutions of k, 0.1, 0.2, 0.51, and 10. The hypersonic speeds are around here. Now you'll see from these hypersonic profiles, we'll make some notes. A single wedge shows the best performance. The double wedge, like the diamond airfoil at supersonic speeds, is the worst performance. Pressure rise across the shock will always be much greater than the recovery through an expansion of an equal turning angle. Therefore, aerodynamic forces must be influenced by pressures of shocks alone, and the expansion waves provide little aerodynamic benefit. We do not want shocks to radiate from the upper surfaces because they create huge pressures on the side and the top of the vehicle, which forces it down and reduces lift. This is, of course, the idea behind the wave rider, that we want to have large and strong shocks on the bottom and expansions on the top so we create maximum amount of pressure lift. The best profiles, therefore, will have flat lower surfaces as shown in this particular wedge case for an ideal coefficient of lift at high K and low alpha. Let's look at some more select experimental results, which we compare with our newly developed hypersonic theory. On the y-axis, we have coefficient of lift. On the x-axis, we have indeed alpha. The linearized theory is pointed here as a simple straight line. The characteristic theory we developed earlier is shown here, and the hypersonic theory, which we newly developed, is the dashed line. Experiments for this shape is shown as dots, and indeed the hypersonic theory has the best agreement. Here's another case at Mach 6.9, but for the coefficient of drag. On the x-axis, we have angle of attack, and y-axis, we have the drag coefficient. This is double wedge profile with a delta and square planforms, which we showed pictures of on figure 458, here and here respectively. Once again, these experimental values follow best the hypersonic theory. Now we might show ratios of lift over drag on the y-axis and angle of attack on the x-axis. Let's look at these same planeforms of the double wedge profiles and square planeforms at Mach number 6.9. You'll see the inviscid theory completely diverges from the experimental results, especially at low angle of attack. The triangles and circles, of course, are experimental measurements. Indeed, the best theory follows the hypersonic theory once again. Let's look at how, of course, our pressure varies on the surface of a vehicle with varying Mach number using hypersonic similarity theory, which we developed. On the x-axis on the right, we have m infinity. On the y-axis, we have coefficient of drag. Here, you can see the line is theory and the dots are experiment. There's almost perfect agreement for a theory. On the left, we show p minus p infinity all over p infinity for the same theory and experiment. You can see there's a huge rise across a particular shock wave, which is just above the bend in the cone. This shock wave pressure rise is predicted almost exactly by, of course, the theory of the oblique shock wave for hypersonics, which we just developed in this class. In this class, we have reviewed the major theory and developments, but not in detail, which you can do on your own by finding documents on NASA Technical Report Server or the original writing and derivations of Dr. Cien. These are all found easily through Google. We looked at the original theory, of course, of Isaac Newton, who, of course, created the corpuscular theory. And, of course, as certain assumptions in Dr. Cien's theory, like gamma equals 1, we can recover his theory exactly. But, of course, gamma is not equal to 1 for the realistic flows. Indeed, we have derived K, Ks, and K theta, the hypersonic similarity parameters, for, of course, the standard flow, the shock wave, and the expansion wave, respectively. These are related through affine profiles from experiments to actual flight vehicles or from CFD. We derive the isentropic relations, the oblique shock relations, and the expansion relations and show their comparison with respect to traditional measurements. Indeed, this theory is revolutionary, very complicated, but very, very useful, because, of course, it created the basis of hypersonic theory in the world. Thank you very much for your time today. I'm Professor Steve Miller.